Okay, let's continue. And as sessions before, I'm going to start by firing up our studio. And the first thing I do is to open my project to make sure I'm in the right working directory and I'll be able to find my data right away. So these projects, here it is. And our studio restarts the R session, setting the work directory as needed. And so we're going to learn how to calculate correlations and do some very simple linear modeling in R. But before that, I would like to have a quick look at this data set. Oh, what I'm going to do is I'm going to, let's see where I'm at, S05. So I'm going to create a new script, file R script. I'm going to call, save it, and save as S06 L for linear modeling. R. So that's the next script as part of this module. It is, so let's have a look at this data set, composed of 8 columns, and this represents 4 data sets. So x1, y1 is one data set, it's a pair of coordinates. x2, y2 is a data set, x3, y3, and x4, y4. So we have 4 data sets, each is composed of 11 pairs of y's. And so if we look at these values, there's not much we can say. But if we start to try to analyze it, if we look at the mean of of the first column is 1, the mean of the second, 9, sorry, the mean of the second column is 9, the mean of the third column is 9, the mean of the fourth column is 9, and keep on, fifth one is 7.5, sixth one is 7.5. So if we look at the mean of all our axes, x1 to x4, they all have the same mean. y1 to y4, they all have the same mean too. I'm going to switch to the lecture notes because there is a whole set of other metrics that we can calculate that are shown here. Okay, so from the original data, there is not much we can say. Hardly ever look at data like this and try to come up with some interesting patterns. However, if we look at these pairs of data, there is a clear and very striking patterns. They all have these same summary metrics. And in particular, the correlation, which is one of the topics that we'll explore a little bit during this session, we see that all the x1, y1, so the xi, yi pairs, all have the same correlations. And so maybe that means something that means something interesting. Maybe this means that these data have something in common. But this is a warning. warning that it's very dangerous to kind of judge a data set by these summary values. So we need to be very careful when we look at correlations in particular. So it's a warning that we shouldn't try to summarize too much into this one value, this correlation value. And it's also an invitation to visualize data sets in addition to or before calculating any of these values. And indeed, if we look at these 4 data sets, so here they are. This is data set x1, y1, x2, y2, and so on. We see that they are completely different. And of course, they have been engineered so that they have the same means in the x's and the y's, and the same correlations. So of course, it's a these are not real data sets, but they are, however, really good examples that it's very dangerous to apply any method like calculating correlation and taking these results that we have as face value. And clearly, among these 4 data sets, they all have the same correlation. The only one where kind of a linear fitting would be applicable is the first one. In the second one, clearly there is no linear relationship. There is a relationship between x2 and y2, but it's not linear. The third data set here, there is a clear outlier. If we remove the clear outlier here, these points are on a straight line, so linear relationship would fit. But with this outlier, doing a linear relationship is not very relevant. First thing we need to do is to understand what happens with this point. Clearly, out of line, especially here, but we first need to understand what happened to this point before doing anything else. And here, clearly, also a very specific data set. And so this is a very old data set. I don't remember when it was defined as the Scombe data set. But more recent examples of these data sets that have the same summary metrics, but are actually very different, can be seen here, and the link is in your data set, in the slides. So all these data that you see here, you have transition from one data set to another, they all have the same summary statistics. And if you scroll down, yes. So here we see the transition from one data set to another, and the mean of x, y, standard deviations, and correlations are essentially the same for all these data sets, including the dinosaur. So an invitation to make sure that before calculating any value, whether it's a correlation, any type of modeling, whether it's any kind of statistics, p-values, before and after calculating this, look at your data to make sure that these values are relevant. So let's have a look a little bit at correlation and how we can calculate correlations in R. And so I suggest to get started, we load the data set that we used already yesterday, the IPRG data set. But I would suggest that we load one that it's the same data, the same values, but it's formatted slightly differently. And so in my data directory, if I have something called IPRG2 normally, yes. So it's an RDA file, kind of serialized R object. So as it lives in memory with that specific structure, it's written directly on disk. It's not converted to a CSV file, TSV file. And I load it directly as it is from disk with the load function. Okay? And this data, I'm going to use ls to list all the variables that I now have in my workspace, and I have this new variable called IPRG2. And this is how it looks like, so it's a data frame. Maybe I'm going to use str, function that we have seen yesterday, to give us the structure. And so it's a data frame. It has 3027 observations, so rows and 12 variables. And what we have is these rows are, we see here, part of it. Maybe, well, we could use view. Not used to view, but that's probably the easiest here. RG2. So it's the same data set as we had yesterday, but it's formatted differently. We have the proteins along rows and the different runs or samples here along the columns. Okay. So it's not a tidy data set, or not tidy as in as we have to find it, but it's a data structure that is found very, very often in omics data analysis. Generally, that's how we have this data when we do RNA-seq or quantitative proteomics. And it's a very handy format. So it's not necessarily the one that suits the ggplot2 or dplyr, but it's very handy, very useful. One advantage of this data set, for example, as opposed to a tidy data set, let me load going to load the other data set. And the file is data IPRG summary. So here I loaded the data set as we did yesterday with read.csv. So that's one format. That's the other one. One really huge advantage of this one is for missing values. Okay. So I would immediately see if I had a missing value for this protein and that sample, right? Because I would have an A there. So it becomes immediately clear where I have missing values, and I can easily see patterns in missing values. Do I have more missing values in one sample than in another one? Or do I have a certain protein that has many missing values? Okay. This is immediately obvious with this data structure, but not at all here. Actually, if we were missing this line, because there was no intensity recorded for that sample and that protein, we might not have that line at all. Okay, so we might not have any missing values in this table, and yet miss some intensities for some samples and some proteins. Yes, that's a question. And none of these is better than the other one. These are just different ways to encode the same data, and some data structures are more appropriate for some analyses, some visualizations, and other data structures are more appropriate for other applications. But now, for this part, I would like to use this data set because we will want to access the quantitation values of these columns for 3 samples. That's what we're going to use. And so I'm going to create a new temporary variable x based on RPIG2, and I will limit myself to, these are the same ones, column 1, 2, and 10. Okay, so IPRG2 is a data frame. I want all my rows, but I want to limit myself to columns 1, 2, and 10. I'm going to use hat x. Okay, so these 3 samples, sample 1, technical replicate A and B, and here we have sample 4, technical replicate A. And we have these log2 intensities for these 3,000 or so proteins. So one useful function when we have a limited number of samples is pairs.
that will take, here we have a data frame with 3 columns, and it will do all possible pairwise scatter plots. So scatter plot between sample first one, 1A and 1B is shown here or there. Scatter plot between sample 1B and 4A is shown here, and scatter plot between 1A and 4A is shown here. And that's kind of the first plot that we will want to do if we want to look at the correlation of these samples. Okay. So that's what we see. Do these 2 samples correlate? If they do, they are on one line. And if we indeed identify that there is a correlation, or if it's worth starting to compute these correlations as opposed to the data sets that we had before, then we can start and calculate these respective correlations. Pairs is a function from the base graphics. So it's not a ggplot2 function, but it's really handy. Maybe it's not the most beautiful representation, but it's super handy to quickly create all these pairwise graphs. So know that we have seen that these data sets are appropriate to calculate the correlation. We can do that with the function core. That's the function in R to calculate correlations. And if we give it 2 vectors, it will calculate 1 correlation between vector 1 and vector 2. But if we give it, for example, here a data frame with 3 columns, it will calculate all pairwise correlations. Okay, so that's what we can do with core X. And here is the result. So what is our result? Anyone? What does this result mean? Pardon? That there were missing values, like what we mean. So the correlation between sample 1A and 1A is 1, but for all the other ones we have missing values. So maybe the first thing to do is to check the documentation of correlation and see if there is an NA.rm. So here it is. Here's our function correlation. So it takes either 1 or 2 inputs, either x and y if you have 2 vectors and you want to have the correlation between x and y. And if we only provide an x and the y is null or missing, then it will do all pairwise correlations. And here we have use everything or different types of correlation. Pearson, Kendall, also here. So let's see, what does the use here mean? For that we need to go down and look at the arguments section. And if we read use, so there is an A.rm here, but that doesn't apply to core. And A.rm applies to var. We want to calculate the variance. But there is a use here, so let's look what use means. So it's an optional character string giving a method for computing covariances in the presence of missing values. Okay. So the default is everything. It tries to do everything, and in case of missing values, it will return an A. Or we can also use all ops for all observations, complete observations, and a all complete or pairwise complete ops. So I suppose pairwise complete ops would be what we want, so we can try. Core X use equal for complete ops. Let's see, let's try to run this. Okay. So here we go. So the complete ops here will only use complete observations, but for pairwise comparisons. And so here are the correlation that we get. Correlation of 1, of course, for the same sample. With 0.97, we correlate 1B to 1A, and slightly smaller correlation, 0.95, so for sample 4 and sample 1, and so on. So we can use the use parameter, but another approach would be to use the NA-omit function. So X is a data frame, and if we pass X to NA-omit, we will get a data frame. Let me review this. get the data frame, but with all missing values removed. All rows with missing values removed. So depending on what we want, we could also calculate correlation with our X with all missing values removed. Yes?
What was complete ops? What class?
So complete ops is not a variable. This means this is a parameter that we pass to call, to the correlation. So correlation, in the first instance, we ran correlation with one input, which is the data frame X. But that didn't work because of missing values. So now we run correlation again, and we pass two inputs. The first one is X, our data frame, and the second one is where we specify use. That's a parameter, one way to parameterize our function, and instead of using the default, which I don't know what it is by heart, we say, well, use only complete observations. So that's one way to tell. It's the equivalent to mean where we had NA.rm. But for some reason, in core, it's not NA.rm, whether we set it to true or false. It's a different way to parameterize this function, and here we say use equal complete ops. And the default is something like all observations, and it takes everything, and if we have a missing value, then the result will be missing value. Okay, so there is no variable use in our workspace. Use is only something that, it's an argument, it's something that lives inside the function, and we want to set it to complete observations. But another way would be to say an a.omit x, and actually that's what I'm going to do here. I'm going to create a new variable x2 because I will need to reuse these data, and I want to get rid of missing values. So I know that I have this x data set, I have missing values, and I will want to do a few analyses, and I want to get rid of my missing values. Okay? And I might lose some data points, because if I remove rows with missing values, I will most likely lose some intensities included in these observations, but I'm fine. There are not that many. Actually, before doing that, let me I still have my x here. Before doing that, I should probably show you a couple of functions, NENAX. Okay. NENA is a function that will check inside x, whatever x is. It could be a vector, it could be a data frame matrix, and it will tell me whether there are any missing values. It doesn't tell me how many there are, but it tells me whether there are any missing values. And very often that's all I'm interested in. Are there any missing values? Before, for example, calculating the mean, I might want to check this manually. So NENA is very useful. Another function that we have already seen is isNA. Okay. So the input to isNA is a data frame. What are the dimensions of x? Let's check. Okay. So we have 3,027 rows and 3 columns. Okay, first dimension, second dimension. So x is a data frame with these dimensions, a data frame of numbers, of intensities. If now I pass x to is.na, what will I get back? What will I get back? Let's look. What's the class of this? Let me first check class of x. Okay, it is indeed a data set, a data frame. And so the class of is.nax is not a data frame, it's a matrix. But a matrix is like a data frame. Okay, it's a kind of a two-dimensional structure. The difference between a matrix and a data frame is that a data frame can have columns of different types, characters, factors, numbers, whereas in a matrix, everything has to be the same. But what is important is that if I look at the dimensions of this, we still have the same dimensions. So it's the same rectangular data structure, but the difference is that let's look at hat. Okay. Instead of having numerics here, I have logicals. And for each cell, this logical tells me whether I had a missing value at this position. In this case, I did not. And there are some cells in there that are true because I had missing values. I know that because when I ran any and A told me true. So what I can do here is to say table of is an A, and table will count how many falses and how many trues I have. So in this relatively 3027 by 3 data frame, I only have 2 missing values. It's not much at all, and I don't mind to get rid of 1 or 2, in this case 2 lines that have 1 missing value. Okay, so 2 lines, that's 6 values. 2 out of these 6 values are missing, so I'm going to throw away 4 quantitative values, but I don't mind. Yes?
How do I column?
Yes. So, good. So x1 gives me the first column. So I could say is.na. Now this tells me in my first column whether I have a missing value or not. And so I could do a table. And this will tell me in my first column how many are missing and how many are not. So this is something I could repeat for all my columns.
Can I define the range in the bracket?
Pardon?
Can I define the range in the square bracket? Can I say 1, 2, 2?
Yes,
3?
yeah. So everything I did here on X, I could do, let's see. Oops. I could say, well, I don't want to look at whole matrix, but I could say data frame, but only maybe the 10 first features and the 2 first samples, and this works too. It's still a data frame, but smaller. But so this is something I did for only my first column, and I could repeat this 3 times, but if I had 500 columns, it would be a little bit annoying. So in general, what I think is useful would be to say is.na x. Okay, so this returns a new data frame or new matrix with logicals. And so what I could do here is use a function called callSums that will take the sums along my columns. But do you remember that if I convert a logical to a number, the true becomes a 1 and the false becomes a 0? So if I do a sum on logical values, they are all automatically converted to numbers. And so callSum is going to do the sum over all columns. And so this tells me that in my first column, I have 1 missing value because I have only 1 true. Okay. Here I also have 1 true and here I have 0 trues. And if there is a row sum, there is also if there is a call. Well done. If there is a call sum, there is also I said it, a row sum. So I can do the same thing here, row sum, to look, now this is much bigger, but to look, the row corresponding to this protein has 0 missing values. Okay? But because this is a little bit long and not very helpful, I can now do a table on this output that tells me that I have 3026 rows that have 0 missing values and 1 row that has 2 missing values. Okay, so I have only 1 row with 2 missing values. So by throwing that row away, I only lose 1 intensity. So actually kind of with is an A, table, callSum, row sum, and table again. So basic R functions, and some of them we have already seen, like is an A. We have seen the conversion of numbers to logicals. With these 2 additional functions, it's already possible to do a quite interesting data analysis. Okay? Finding out something like that, and the fact that we have 1 missing value in column 1 and 1 in column 2, and this of course scales to much bigger data sets, is already something that is really interesting. So whenever I have a data set, for example, these are the kind of calculations I do immediately. For each column, I count how many missing values I have, and the same thing for each row. And then I look at the table, something like that. This will already help me a lot to get to know my data set. And here, I can confidently say that just dropping missing values will make my life easier thereafter, and I'm not going to miss very much. Okay, so let me calculate my correlation again of x2. And here it is. So very easy to calculate a correlation, but I would like to raise another flag here. I think correlations are very often abused in biology, and correlations are taken as a measurement of replication, which actually I think they are not. Okay. Good correlation does not necessarily mean that we have good, or maybe the other way around. Even if the correlation is not very good, that doesn't mean that we haven't been able to replicate our experiment successfully. Okay. The correlation, we'll look at the correlation of the intensities, but an experiment might be well replicated from a biological point of view. We get the same biological information, even though if we have a pretty poor replication. And I know studies and groups that say, oh, look, we have good correlation, so that means that we are able to replicate our experiments. Of course, it's good to have good replication, but actually, worse replication doesn't mean that the biological findings haven't been replicated. So it's easy to calculate correlations, but I think it's also very easy to abuse them. And actually, calculating correlations is a function of the number of values that you take, right? So if you have a really big experiment with many data points, it's easier to have high correlations than if you have a small experiment with less data points. So it's really important to take these values here. Be careful how to treat these values. And if you're interested in replication, I think it's much better to look at the fold changes of your values. I think these are much closer to the notion of replication that we are interested in biology. So for example, what we could do, I had 3 samples, so I'm going to kind of limit myself to 2 samples here. So I have x2, and I'm going to extract, write this here. So I have a replicate 1, and this corresponds to my first column, show here, x2, okay? So indeed, my first column is a sample 1A, and my second column is 1B. So these are technical replicates. So I have my replicate 1 here, and my replicate 2 here. So now I extract these columns as individual vectors. So this is R1, and here is R2. And so maybe if we're interested in kind of replication, or to what extent our experiments are reproducible, in this case, it's probably much better to do the following. So I'm going first to calculate, also these are log2 values. So if I want to calculate a fold change in log, I need to take the difference between my intensities. And then I'm also going to calculate, so M stands for is my fold change. And then I'm also going to calculate the average intensity. So A stands for my average intensity between my 2 proteins. And then I'm going to plot the following. The following figure, that is generally called an MA plot, and MA stands for microarray because these were they started to be used in the times of microarrays. where here on my y-axis I have my fold change, my log fold change, and here I have my average expression. And whether my fold changes are centered around 0, and how far away, and these are replicates, right? So here I don't expect to see any changes. And the spread of these fold changes will be a much better indication for me whether these replicants have been successful and to what extent my experiment is replicable. There is an interesting feature here on this plot, is that most of my values, my fold changes, are centered around 0, right? That's very good. But we can see a bigger spread towards the low end of our average intensities. Okay, so there is a bigger variability for low intensity features. That's something that you will see very, very often in high throughput experiments. So let me get back here, R1, R2. So these are our two samples. So what we would like to do now is to do linear modeling of R1 and R2. And to do this, we can use the ln function, ln for linear modeling, and we want to model here R2 as a function of R1. And this is something that we can write, it's shown here, R2 tilde R1. So the tilde is part of the kind of function, or this tilde notation in R that allows us to define relationships between dependent and independent variables. And so this is now the simplest way to define these notations, R2 based on R1. Yes?
How do you get that notation?
The tilde. So this will depend on your keyboard. On this one, it's top left. So shift and then the key just under the escape. Between escape and tab. So let me store this in a new variable that I call lmod. So here is lmod. So lmod is a variable that stores something that is not a data frame, that is not a matrix, not a vector. It's a variable that stores the result of this linear modeling. And we can look at the summary of this model. Write this in the script here. Summary, lmod, and here it is. So it reminds me of the formula that I passed. Gives me information about the spread of my residuals. We're going to see in a second what this is. And here are intercept and slope. And so if we want to look at what this result of linear modeling looks like on our figure, we can use the APline function. So APline is a general function to plot lines. It's here. So for example, let me come back to this figure here, my MA plot. I can use APline to plot a horizontal line at 0. I'm going to define the color equals red, so it's a little bit more visible. So to draw this line, I can use APline, H equals 0 because I want a horizontal line that will cut Y here at position 0. Okay, so APline. I could also use an APline and then change this to V equals 22, and let me change it to blue to produce a vertical line. So that's what this APline function does. So that's a function-based plotting. So this is not the kind of things we could do with ggplot2. ggplot2 would need to create an object, and then there is a geom line, or geom Vline, geom H line that we could add to the plot. But this is space graphics. Okay. So that's how APline works. We can draw a vertical line, a horizontal line, or what we can also do is to say, well, let me reproduce my scatter plot here. We can also say APline is clever enough to know that if it gets as input an object that was produced by LM, it knows that this line, or it knows how to draw the line that is the result of a linear model. And I'm going also to specify the color here. And so it will draw that very specific line that has been generated by our LM function. Yes?
Is there an easy way to plot the line that would indicate perfect correlation?
Yes. We can use APline. And the first argument is where this line should cut our x-axis, and the second one, the intercept, and the second one is the slope. So let me say here color equals blue. So here it is. And here I use 0, 1, but then you would define the intercept and slope as you need. And another one that I find useful is grid. And that produces this grid. And indeed, you can see that the blue line goes exactly through the grids. But there is another really important point about models in general and linear models that refers back to the very first example that I showed with the Anscombe data set, where we had 4 data sets that all had the same correlation. But when we looked at them, here they are. Clearly, these were very different data sets, and actually only the first one was fit for linear modeling and not the other ones. And another way to look at this, or to realize that this is an appropriate model for linear modeling and the other ones are not, is to look at something called the residuals. And this is something that we can do if we ask to plot our model. So when I say plot a LM mod, actually this plotting will produce 4 different figures. So here in my R console, it asks me to press return to produce the first plot. And what we see here are on the y-axis the fitted values, okay? So the estimated values after our modeling. And on the y-axis, we see the residuals. And the residuals is the difference between the fitted value and the actual value. And what is always expected, one of the assumptions of our model, is that the distributions of these residuals is normally distributed around 0. Okay? And this is like the MA plot that we had before, actually, or it looks very similar in shape. And we expect to have all our values, there are residuals, the difference between the actual value and the predicted value, to be centered around 0. And then, of course, we have some spread, but it's centered around 0. Most of our values are here, by definition. That's what our model does. But the spread of these residuals is symmetric above and below 0. And there are a set of figures that allow us to explore these residuals. Same thing here. Or for example here, So the leverage, so again here we have our standardized residuals. Here a leverage, and the leverage is a value that tells us to what extent does one point, so for example, this one or that one compared to that one, have an effect on our linear model. So if I remove one point, is it going to influence the result of our model a lot or not? So for example, let me come back here. Let's look at this example here. If I remove this plot, do you think that my model will change? If I remove this plot, will I still have something close to this line or something pretty different? I will have something pretty different in the sense that my line will exactly go through all these points. Okay. Now let's assume that, so if we looked at the leverage of all these points, this one would have a big one. Because if I remove this point, my model will change a lot. Okay, now let's assume that I don't have this point, and I repeat my linear modeling, my line will be exactly through here, okay, through all these points. I can remove any of these points, and my linear model will remain exactly the same. Okay, so that will be to have a leverage of 0, so very small, a 0 leverage. So if I come back here, this allows me to see what points will influence my linear model. Again, here, my residuals. And what we see here is this Cook's distance, which, if I remember well, is also a measurement of what's the influence of these different points. Okay. And so this point here would have the biggest influence, but I don't know where this threshold of 0.5 comes from, but they are still kind of within the limitations or the kind of reasonable limits based on this Cook distance. And so looking at these kinds of plots, whenever we do a model, we can't just take these values that are spat out as they are. It's important to visualize the data and to do a quality control of our model. And this can be done here with plot of plotting the model and inspecting the residuals. And so to wrap up this part on correlations and linear modeling, I want to repeat this figure. Or figure very similar to this one with ggplot2, right? So what do we need to plot this figure? We need R1 and R2. And then we would also need the results of our linear modeling. Okay, to repeat this. But to be able to use ggplot2, we must have a data frame. So I'm going to create a data frame. I'm going to call it DFR here. Data.frame. So if I want to create a data frame by hand, we haven't done that yet. We created our data frames by reading some data in. But if we want to create it by hand, we can use the function data.frame. And then what we pass to these functions are these individual vectors that will constitute the variables or columns of our data frame. And so what I want to do here is I pass R1, R2 to create this new data frame. Actually, I could use I could use the X2 or the X value that I had before. But this is an opportunity to show you here at how to create these data frames by hand. Okay, because I want to use ggplot2 now, so I have my data as two vectors, but before using ggplot2, I have to convert this back into data frames, into a data frame, otherwise I cannot use ggplot2. Okay. So DFR is my data frame that holds my data. And now I can use ggplot2. So how can I produce this scatterplot with this DFR data that contains two columns, R1 and R2? So I want to do a ggplot figure what do I start with? Yes. ggplot. What else? What do I need to feed as input to ggplot? The first input is
Access. AS.
axis, data frame. I'll start with data frame. Okay, and then the second thing, I mean that's the order. I could also swap the order if I wanted, but then I need to do the mapping of my axis. How do I do that? What function do I need to use?
AS.
A for aesthetics. Yes. Right. So I have a x and y axes. So what do I want to map to my x-axis? And it is indeed one of my variables, my columns, and to y are 2. And so I can already execute this. Oh, okay, I have this error. What do I need to fix? What do I need to do to fix this error? Yes. ggplot2. So I could also say library tidyverse, and then it would load, I don't know, a dozen or so packages, but here I'm only interested about the functionality in ggplot2, so I say library ggplot2. I run it again, and so this is what I get. R1, R2 with the axes, and indeed this looks like the range of values we had for R1 and R2. And what else do I need here? I need to specify a geom. And what geom do I need to use to plot points? Geom points. So here we go. I can execute this. And now I reproduce here the scatterplot with ggplot2. And it arguably looks a little bit nicer than base graphics. We could very easily change the circles of base graphics to full points with these little details. So here we have repeated or replicated what we had here on line 44 with the specific ggplot look and feel. And so what we also want now is to add the linear modeling line. And actually for that, ggplot is really nice, because among the geoms it has one that is called smooth. So it can automatically do some smoothing for us. And the method that we want to use here, method equals lm for linear modeling. And so here it is. So under the hood it's the same thing. ggplot2 is going to use the lm function to model R2 as a function of R1. So here, as long as we have a data frame, these 3 lines of code will use ggplot2 to produce a scatter plot and draw the linear model, which is these 2 variables. If we were to use base graphics, we use plot R1, R2, we do our linear modeling by hand, and then we call APline Almont. And something else that we can add, so we're not going to see very much here, but we can also use another geom that is called Quantile, and see here I'll say color equals red. And yeah, we don't see anything here, but what we can do, so the Quantile will actually produce 2 other lines that run parallel to the blue one, and that will give us an information about the quantile, kind of the strength of this linear model. Right? This is one model, but the line could be a little bit tilted up or down. So this is the optimal line, but there is always some variability when we do our model, and so we can use geom quantile to overlay to this model confidence interval around the model. But here we have so many points and it's so nicely linear that we don't even see this. Actually, let me try, if instead of TFR, I use X, let's see, names X, and here I take some, because these ones are slightly less correlated. Let's see if I can get some variability in my model. Huh? Let's see, class X. It is a data frame. I think I know why. Let's see if I. Okay. Right, so what I did here is that I repeated this plot. So do you remember my data frame X that had 3 columns? So I reused this one, and then I mapped to X my first sample 1A, and to Y sample 4D, and I repeated exactly the same. And I hope to see some variability, but again, we have too many points, and the model is very, very accurate. Actually, and the error that I had before was because these are not valid variable names in R. You cannot have a dash in a variable name because this looks like a minus. So if I try to create a variable, a-b, and assign it 1, I get an error because it tries to say a minus b, and there is no such thing. And so to get around this, I use the backticks. But so clearly these are kind of bad names, or not very informative. Maybe it would be better to call this as sample 1A, sample 4A, so on and on. So as an exercise, I would suggest to do the following. Using ggplot2, repeat the MA plot. So feel free to experiment with what I have done. All the code is shown in the notes. So what you could do is to repeat some linear modeling and calculate the correlation of maybe 2 other samples. But otherwise, what I would also suggest that I think would be an interesting experiment is to repeat the MA plot that we did here, okay. And try to do that in ggplot2. So you have the values already, a and m, but these are 2 independent vectors that you cannot use straight away as input for ggplot2. So how would you do? You know what geom to use, the geom point. These are individual points. But from these 2 vectors, m and a, how would you proceed to use ggplot2? And you can get some inspiration from these lines here. So do you all have sticky notes? If not, could you pass these around and take one if you don't have, but I think most people do. Just to let me know once you are happy with this ggplot2 exercise, and we can possibly move on to something else. So here is my MA plot, exactly the same one I had before with my M and A values, but here I use this geom, which is H line y-intercept equals 0, which is the equivalent of APline v equals 0. So here's where I expect all my points to be centered around. Now, I could use do a linear modeling, but maybe in this case, I don't want to do a linear modeling. I don't want to model m as a function of a, but the kind of modeling I would like to do is the following one. So kind of what I want to use is a sliding window approach. And where I'll do my my regression in a sliding window approach. And this is not a linear method, as you can see. So here's my result, and it can show me if I have variations in my model along my my average expressions. And so this could also produce something like this if the data were very different. Okay. So here I don't want to use a linear model. I don't really want to see if there is a trend up or a trend down, but I don't want to use. I want to use this lowest stands for. Question mark was local polynomial regression fitting. It's not how I remember it.
It's a logistic regression. Logistic regression, right?
It's not a logistic regression. No, that would be logit. Okay. Local weighted. Okay. Locally weighted polynomial regression. Okay, I knew there was a locally weighted. And I think the lowest with a W or without are actually the same. We can see if we can use W here. So this one requires another package. I'm not going to install. Anyway, so if we wanted to model this MA plot, we wouldn't want to use a linear model, but we would want to use this local smoothing that uses this kind of sliding window approach. Okay. So it would start here on the left, and then it would take the average of all my points here and draw a point. So here at the very left of my graph, my average is slightly lower than 0, and then it goes up and it's slightly up. But in general, I have a really good fit. All my points are centered around 0. And here we can see that we have more uncertainty about this kind of local fitting. We're not quite sure at the left, at this end, whether it's really 0 or a little bit at the top or at the bottom, but that's because we have less points here. But we can see that here, where we have a very dense cloud of points, it's very close to 0, and with very little uncertainty in our model. And then when we reach the other end, we have less points, great uncertainty. So here we see the output of G on point 1. Any questions about this part, what we have seen now? Okay, so I want to briefly to talk about this anymore. And for that, I'm going to open a new script, new file, new R script, and I'm going to call this S. Also save this S07. And send this. And briefly talk about a package that we're not going to look at in great detail, but just I want to show that some of the things that we have learned here in the introduction to R can be readily applied to more complex data structures. The concepts that we have learned can be reused in more complex data structures. And the example that I'm using here is mass spectrometry and quantitative proteomics data, but the same principles could be used if you do transcriptomics data, if you do RNA sequencing. And so I'm going to briefly data, briefly cheat and quickly go and add patient data and copy some code here. Go copy some code here from these example files to quickly get two files, very small ones that come with the package, because of course we're some larger data sets with larger files. The base name function will only return the file name and not the whole path to the file. So I have two file names, one that is called Quantile and one that is called ident file. And these two files come from an iTrag experiment, but it's called dummy iTrag because it's very small. One of them is an MZ-XML file, and the other one is an MZ-ID file. So this contains raw mass spectrometry data, and this contains identification results in the usual horrible XML files. And so, just as we have seen read.cs, oh, I see plenty of words sticky notes. Do you have questions? Okay, oh, if you, yes, okay, so, good point. So if you don't have package MSN base, you need to install it. So MSN base is a package that comes from Bioconductor. Bioconductor is this project that was started, not sure if it was 2000s or slightly before, by Robert Gentleman, who was one of the original authors of R. And so all the R packages live on CRAN, Comprehensive R Archive Network. So that's the kind of big repository of all, where we have tens of thousands or probably more packages. And Bioconductor is a package that is dedicated to the analysis and comprehension of high throughput genomics or omics data. So it's a project that is separated, so the packages are not on the CRAN, but they are on these Bioconductor servers. And to install Bioconductor packages, we need to use a function in a package called BioC Manager, and the function is called install. And it's not install the package. Install the package is going to look for packages on CRAN, but here we have packages on Bioconductor, so we need to use a slightly different function. That uses install the packages under the hood, but this function knows that it needs to look for these packages first in Bioconductor. And so we need then to say install the packages in MSN base, and that function, exactly as install the packages did yesterday, it's going to look for this package in MSN base in Bioconductor, and it's going to install that one plus all the other packages, all the dependencies. Okay, so if some of you, it will take a little bit more time to install because there are many dependencies that need to be installed. So if you have issues installing it, I'm happy to do debugging one by one during the break, but we don't have much time, so I want just to show you a few things here. So this line of code should install it. During lunch break, I ran BioC Manager install MSN base on this computer, and it worked without any problem. Right, so I have a Quant file that contains an XML, XML file, ident file contains an MZ ID file. So just as we had read.csv, there is a function called read ms data to read mass spectrometry data, either in MZML, in MZXML, NetCDF, and all these fancy formats. And it will detect these automatically for you. So we can say x read ms data, and this will produce a variable, but this variable is not a data frame, it's not a vector, it's a variable of a specific class that we can ask for. The class of x is MSNX, and it's a special type of class of object that is meant to store mass spectrometry data. And so it's a tiny little data set where we only have 5 spectra. They are all MS2. The retention time is between 25 minutes, 1 second, 25 minutes, 2 seconds, and so on. But this could be, we have used this to load hundreds of MZML files. And we would need to change one option here, but so this is a small data set later on. And so we have seen that to do some subsetting, we can use the square bracket operator, like this one. So we haven't seen lists. And if we had seen lists, we had seen that in some cases we need to use a double square bracket operator, which is what we need to do here. But if now I say X, and I use this square bracket operator, that is the operator to do subsetting, and I say 1, I extract my first spectrum out of this raw data that had length 5 spectra, and now we extract the first spectrum. So I can use another function that says add identification data X. This is my raw data, and my identification data comes in this MZ-IdentML file. I can execute this, and now I have an updated X object, but that also contains the identification results. And if I remember well, these identification results were generated using MSGA+, but it doesn't matter. You can use any search engine as long as you can export the data in MZID. And so there is a function called fdata, and I'm going to feed this into view immediately so we can see what we have in detail. Fdata is some annotation of these 5 elements that we have, 5 spectra. So what kind of annotation do we have? We have the acquisition number of these spectra, 1, 2, 3, 4, 5. We have their sequence, if they were identified. So the first spectrum is actually a PSM that has this sequence, that sequence. Spectra 3 and 4 were not identified. So we have an ACE, we have the charge state, with a plus threshold, and so on. The usual kind of information that we have from identification of PSMs. So I mentioned that we can extract one spectrum, and this infrastructure is aware that this data is on the data frame, but it's a special type of data, and we can plot a spectrum. So here it is. So it knows how to extract the M over Z values and the intensities of an object of class spectrum, and it will produce a spectrum like this. And so if we know that this is, for example, an experiment that was quantified with iTrack 4plex, we can also ask it to plot the spectrum, but also highlight the 4 peaks that are here corresponding to the iTrack reporter ions. So using functions, the plot function that we haven't seen explicitly, but we have used it kind of naturally, feeding it a vector or matrix, and plot knew what to do depending on what kind of input it had, while this plot function knows exactly that if its input is an object of class spectrum, it knows how to plot it. And so it's possible also to take this raw mass spectrometry data and quantify it using the quantify function, but I'm not going to do that now. I'm going to immediately load another object that is called an MSN set that now stores quantitative proteomics data. And so as we can see here, we have 55 features. Again, it's a small data set that comes with a package for 4 samples. So it's essentially like a data frame with 55 rows and 4 columns. And we can extract these intensity values with a function called exprs. So here they are. These are the 55 by 4 quantitation values. Here they are for my 4 report ions. But in addition to that, I also have, so here I use the same function fdata to extract the annotation of these features. Oh, yes. I want to view these. So for example, here we have 55 peptides, so we have 55 lines of annotation, and the first spectrum belongs to protein BSA, that's the protein description, that's the peptide of that sequence of that peptide, attention time, precursor, and all that values. So we can store the different bits of this quantitative experiment, the intensities, the annotation of our features, like shown here, and so that was with F data, and the P data shows us the annotation of our samples. So here we don't have much. We know the MOZ values for these reporter ions, and we know that these are ultra-4 plex, but we could add additional information about our samples, including our complete experimental design. Maybe we have condition control and disease, we have technical replicates. So all this information can be added to this data frame to completely document or describe the experimental design corresponding to this data. And so let me come back to EXPRS. So we have seen the square bracket operators in the frame of the data frame, and these behave exactly the same way. If I want to have my 5 first features, in this case PSMs, for samples 1 and 3, I can reuse what we have learned yesterday, but on this object. And these cryptic symbols that we have learned about with data frames generalize to other types of data. Okay, so this is kind of the next step, kind of things that you could explore and learn about based on what you have seen during this introductory course. So a whole world of cool power packages and exciting analyses that are ready to be explored. There is in terms of Amazon base, there is the Amazon base webpage here, and you can find it if you Google Amazon base and some documentations here, and there is plenty of documentation, plenty of things that you can do. So this with raw data was here. We produce this three-dimensional visualization of your raw mass spec data, MS1, and a set of MS2 spectra in between, and so on. So there are lots of things that you can do. Always, of course, new packages, new functions to learn about, read S data, identification data, but the principles that you have seen today and yesterday equally apply to these more complex objects exactly the same way as we have learned them on data frames. So these principles that we have learned in R, they apply to many, many other use cases for omics data, proteomics, RNA-seq data, and so on. Okay, so I think it's time to stop and have a break, unless you have any questions. So yes, we had a vote yesterday, and the overwhelming majority wanted to look at linear models and correlations. So for those that want to learn a little bit more about combining different data sets, I'm going to write that URL down over there. That cryptic code is the identifier of Quantile. And if you look at the chapters here and you look at the chapter joining table, there is a chapter that describes the basics of how we can join tables, in different ways, depending on their columns that they have in common. I think that chapter is a good introduction. It's typically the kind of material I would give if we had 30 minutes or 45 minutes anymore. But I think it's well described, so if you're interested in that, you can have a quick look at that chapter. And it's chapter 6. Okay, so that's all I wanted to say. And we have our coffee break now. Thank you very much.